I'm going to be talking about the data and analysis. Essentially, we work in credit scoring, which basically means that we have different views on modelling than some statisticians might have. And generally, in credit scoring, particularly in the retail side rather than the business side, we have vast amounts of data. In the context of this study, we have very limited amount of data. We've only got 445 companies were considered. They've got to have survived 3 years. We're trying to get rid of early failures. A lot of companies fail within the first few years, so we try to get rid of those kind of failures. And we looked at 2001 as our financial ratios in 2001 to try and predict the performance to the end point, which is 2004. Now, as I said, there are huge differences between statistics and credit scoring. And primarily, they're interested in what are the variables, and essentially, that's part of the concentration of this talk, looking at the variables. But given that we have got so few defaults quite regularly in the data, we decided that we wouldn't look just at companies that defaulted, but also companies where they actually were in financial distress. So we took two other definitions of distress, and the insolvency ratio and the interest coverage, as giving us 4 categories that we were trying to look at. So we're not just looking at healthy and default, but we are looking at 2 other categories as well. So how many have we got in each of these groups? Well, there's 28 in the dead, 32 in flow-based, stock-based distress, and 57 in just flow-based. So 157 in that, and the rest were active. Now, this number will go down in some of the analyses because some of the information is limited. We started off with financial ratios over a whole series of types. So we've got 9 classifications, and we finish up with about 70 variables. So there's 70 variables which are highly correlated. Highly correlated. We are going to use, through parts of this talk, area under the curve, which is looking at the sensitivity against 1 minus specificity, and the closer you get to the top is supposedly the good situation. Now, there are several authors which have pointed out that this is actually quite a poor measure. Most recently, David Hand has indicated that this is a poor measure. But we're going to use it in this presentation. We do look at other measures in the work that we've been doing, but this is the one we'll concentrate to a degree in this presentation. Logistic regression. The paper in 2007 really covered this area in greater detail. And what we were trying to do is look, using logistic regression, at various kinds of groups, looking at those that are dead against those that are healthy and don't have any distress, looking at group 4 defined as good and all others groups defined as bad, groups 1 and 2 as bad, and opposing group 3 to 4. So we've looked at 4 different models in some senses, but we've also looked at other aspects, which is the full model, a full list of the original untransformed ratios. So that's the raw data. And then we've gone through a whole series of other models in this context. And the ones which we'd like to pick out are the ones which are cost classified. This is something that is regularly done within credit scoring in order to allow a certain amount of non-linearity into the model. And to show why we're doing that, here is the cost classification of cash flow And essentially, as you can see, there are non-linear patterns occurring in these particular diagrams. So here are some of the results. I'm not going to go through all from A to F at the present time, but the thing I'm trying to show here is choice of which groups you take against which, and what kind of use of the variables you make is having quite a major effect on the variables that actually perform in this particular context. We don't get one consistent set of ratios. In terms of performance, the best performance overall is model E when we combine 1, 2, 3 against 4, and I don't think that's particularly surprising, because what we're getting towards is a balance in those classed as bad against those classed as good. So I'm not surprised at all that the performance is the best in this column in some senses. It's nice to see that course classification has the effect. If we move to 1 v the rest, so things that aren't dead, then we still get a course classifier model, but the area under the curve goes down considerably. Of course, if we've got 4 groups, what we should have been doing is using ordinal regression or multinomial regression rather than just what we were previously using. Of course, we have a problem in this context, and the problem is very straightforward. If you have course classification, that means you've got a set of categories. And we've got a large number of variables that are potential, and what we have discovered, because we've got very few deads, is that we do not necessarily get convergence with ordinal regression. So the only model we've really looked at is the raw data fit in this context. The issue for me, when you actually look at this is, we've got 4 variables. There is obviously some overlap with some of the models we've used previously, but those of you who are quick enough to spot, there's obviously something going wrong here with the high variances associated to the 2 of these variables, 1 positive and 1 negative, and they're slowly getting larger and larger. Again, indicating one of the problems that is inherent in a data set where you've got considerable amount of correlation between the variables that you're trying to fit. The other wonderful thing about the ordinal regression is that it's not achieved a predictor for group 2. And the overall prediction is not particularly wonderful either. The overall prediction is fairly poor. Multiple regression, well, multiple regression is less restrictive, but still suffers from the problem of we can't really use course classification easily in that. We still have problems with convergence. But, of course, each category, compared to the base, might bring in a new variable. So what we see, if we suddenly increase the number of predictors, and they may be only coming in for 1 group, and in some senses, one might be very concerned that we're overfitting in this particular context. The performance here is, yes, we do get group 2 being at least predicted, but we're not still achieving vast results in this context. We started thinking, let's go and look at other alternative methods, survival analysis. We have got age on the company for many of the companies, but not all the companies, so we have to reduce the data set to some degree. And I think what really surprised me is that we've got some small and medium-sized enterprises that were lasting 150 years. And the family business is continuing many generations, which is rather unique in some senses. Again, we're getting a set of variables that are reasonable in this context. However, we've got a small data set, so one of the things we've been doing throughout the analysis is doing tenfold cross-validation. And the interesting aspect of that, if we go past these diagrams, is that we can actually see two subgroups developing. One, the majority subgroup, and then the other one appearing. Again, this is because of that high correlation between the variables, and what we're getting is obviously an indication of multicollinearity and the changes. We thought we'd throw in Merton just to show how wonderful applied mathematics is with your dear old stochastic process underpinning. And we've got there the dear old logistic results. And here is the Merton model rho, which is diabolical. It does not predict very well in this context. And one of the reasons for that is small and medium-sized enterprises, if they are traded very rarely. So you don't actually get a true representation of the volatility. So it's not really condemning, it's just saying we haven't got a proper estimate of the volatility in the price of the company. Problems? Well, as I said, this is relatively a small sample. We're usually in credit scoring talking about 20,000. We've clearly got a problem of multicollinearity. Choice of modelling framework in this particular case, and I don't want to generalise it because in a lot of other cases in credit scoring it's not the case, but in this there does seem to be quite radical changes in the set of variables that you would put in, and that sometimes worries me. And I think we need considerable amount of work before we could actually say what we would define as the best model. I mean, area under the curve is not a brilliant measure. We'd have to investigate much further. And there are a whole series of different approaches that we could have been using. Fast sparse regression would be another candidate. And Mike Titterington talked about tilting centroids yesterday as being a possible approach. And that's the end. Thank you very much.
I'm from the University of Bristol, and this is a joint work with Guy Nason, where we tried to define and also we propose a methodology to estimate certain relationships between locally stationary processes. Often stationary time series models have been found inappropriate for time series analysis, where data show properties evolving over time. And locally stationary processes, LSP, from here, have been proposed as a generalization where basically the spectral properties evolve over time. And also this is inherited by the covariance function. So instead of talking about spectra and covariance, we'll talk about local spectra and local covariance. We have some evidence that these models fit quite well time series in several disciplines like meteorology, medicine, finance, and economics. And as I said, it can be of interest to define and evaluate certain relationship between these time series. In particular, given two time series in this presentation, we introduce a method to discover possibly time-varying combinations which are stationary. And we call these combinations costationary series or costationary processes. We will consider basically bounded time-varying linear combinations, and we started basically by proving that bounded time-varying linear combination of LSP are still LSP. And then we basically propose a univariate a stationarity test for univariate locally stationary time series. And we basically, what we do is, since we have proved that linear combinations maintain these, are still in this family, we apply this stationarity measure to over the universe of linear combinations and basically numerically optimize this measure of stationarity in order to get a stationary solution eventually. We also show that basically the existence of this kind of solution implies some bounds on the local covariance function. So as an illustration, we analyzed these two time series, which have been analyzed previously in 2001 paper by Starik and Granger. So they are basically two stock indices series, Standard & Poor and FTSE 100. And we started basically trying to, well, in the former paper, Starik and Granger basically concluded their analysis saying that a model with unconditional constant volatility is not appropriate for this kind of data. So for instance, a Garch model is not appropriate for this kind of data. And this led to some discussion at that time. And we wanted to use our stationarity measure to basically see if a locally stationary assumption is appropriate for this data. So what we did is basically we applied our stationarity test on a rolling window on increasing size. And what you expect from a locally stationary process is basically increasing rejection rate for increasing window size. Because analyzing longer series, there's more chance basically that their statistical properties change over time. And from this picture, we see exactly this is happening for this data. Because on the bottom row, we basically use this stationarity test on a window size of 32, and then go to 64 observations, 128. And you can see that when we analyze for 256, we almost all reject the stationarity assumption. And this is true for both series. We can also see that basically a Standard & Poor index is more non-stationary than a FTSE index. And for both series, we basically can conclude that a model with constant volatility is not very appropriate. So we can use our locally stationary processes to analyze this kind of data. And because for a locally stationary process, the Fourier basis is no longer canonical, a variety of pseudospectral representations are possible. And in fact, in the model I use for doing the computations for our application is called locally stationary wavelet process or multi-scale locally stationary process, which is built in terms of wavelets building blocks. In this representation, basically, Wjk over T is the local amplitude function. Psi j is a non-decimated wavelet, discrete wavelet. And psi jk is a random variable, is a collection of random variable independent for each j and k. We define the bounded local spectra as just the square of the square modulus of the local amplitude function. And because this is a triangular stochastic array indexed by capital T, so each row in the array is basically indicate increasing value of T. Because of it, basically, the local spectra will converge pointwise to a function defined in a unit interval. Okay? And my presentation will carry on basically in terms of this function Sjz, which is basically the local spectra for each scale. J is the scale index, by the way. So basically, this model postulates the time series as a combination of components at several scales, increasing scales. Our stationarity test basically consider under the null hypothesis the occurrence that Sj is a constant function with respect to Z, which will represent the time index. Obviously, I must say in the locally stationary literature, we work in the rescale time because these allow for a meaningful asymptotic theory. So basically, under the null hypothesis, Sj is a constant function. Under the alternative hypothesis, Sj is not a constant function of Z. And also, we define the average spectra Sj bar along with this metric, which basically measure the time variation of our spectra with respect to the average spectra. And the test statistics we use is TVS hat, which has basically the same form of the metric, but we basically substitute the spectral entries with their unbiased estimates. Okay. So this is the way we use this test statistics, our test statistics TVS hat in our stationarity test. And it's basically a bootstrap test. We first evaluate the test statistics on the actual time series, and then we compute the average, we estimate the average spectra from the data. And we then simulate using the formula 1. We simulate a realization by setting basically the local amplitude function as a square root of the average spectra. This let us simulate data under the null hypothesis, basically. And once we have this random draw of under the null hypothesis, we compute test statistics under this simulated data, create some random particles, and basically evaluate the empirical p-value by the proportion of particles with greater value than our test statistics, the original calculated on the original data. We have some background theory for this test. And first, we must say that the test statistics I just show you is a syntactical unbiased estimator for the metric we consider, and this is also syntactically Gaussian. And this leads to a number of consequences, such as the empirical p-values we derive in such a way are consistent. So we can basically, under the null hypothesis, estimate the empirical size of the test by Monte Carlo methods, and we can also estimate the power function, the power of the test for fixed alternatives. But this is true for each point in the parameter space, leading to uniform consistency of the power function estimation. But this talk is mostly about costationarity. For illustrate this, I consider two locally stationary processes. In the costationarity theory, in reality, is more general. It doesn't only hold for wavelet processes, but for any process that can be defined in the scale time with locally supported basis functions. But for illustrations here, I consider just the wavelet model. So basically, let alpha and beta t be step functions. In this, in our computations, we consider piecewise constant alpha and beta. But also, in general, the costationarity theory will allow for also more general form of alpha and beta. Anyway, costationarity implies that time-varying linear combinations defined with respect to LSP processes and step function alpha and beta is still stationary. And we basically explore the universe of solutions by numerical optimization procedures. Analytic solutions can be possible, but they will require a solution of very complicated system of nonlinear equations. And at best of my knowledge, it is only possible if the density, analytic solution, if the density of psi jk is symmetric. So if you want to consider more general processes, I think numerical optimization procedure is required anyway. So we just propose the most general numerical procedure. And optimization can lead to a number of solutions, because solutions typically are not unique. There may be more than one. And then we evaluate how different they are, if there are some clusters by multivariate techniques, just to see if the departure of each solution is significant or not. But I will now talk about our solution method, basically. First of all, in our implementation, we consider dyadic segmentation of the time points, basically. So introduce index A, which is the scale index. Index B is a segment index, refer to each segment for each given scale. So a scale 1, you basically split your time points in 2 segments. A scale 2, you have 4 segments. Scale 3, you have 8 segments, and so on. And basically we define PAB as the number of, as the set of time points belonging to each segment within each scale. And PA is basically this joint partition of the time interval, okay? By the way, we define the index B. So we use this notation to introduce our optimization methods. Basically what we do is we define the statistics on each time-varied linear combination we obtain in that way, where the linear combination is defined in equation 7. So basically we have then a measure of stationarity for each linear combination, and what we do is we minimize this test value, actually, not the p-value, but directly the value of the test. We minimize with respect to each possible value of alpha and beta for each segment. And which is very important, we also minimize with respect to the scale index A, because we are interested in the simplest time-varying linear combinations, which are stationary. And basically, we start looking for solutions at scale 1, and then go to increasing scales if we don't find a solution. And we stop as soon as we find such a scale that gives solutions, because obviously we want to have some simpler solution. Obviously, the strength of the costationary relationship depends on which scale we find solution for. In fact, if we find a solution for a very low value of A, means that the relationship is very strong, because these imply just a few structural changes. It's obviously trivial to find solutions for very large value of A, but this will be not interesting from a statistical point of view. So we have an illustration of the two solution sets we find for the stock data. So this is the first set. So after finding a number of optimized solutions, we do some clustering, and we found two solution sets. So we have alpha and beta for this solution set, and on the bottom row we have the actual costationary series, and on the right-hand side, basically we have an estimation of the local spectra with the p-value. And this is the second solution set. So we have alpha, beta, the costationary series, and the p-value and the spectral estimates. We have another consequence of the existence of these solutions. Basically, equation 9 shows the formula of the variance of the costationary series. And working a little bit on this equation, we can find bounds for the local covariance function, with bounds depending on the variance of the costationary solution and on the value of the costationary solutions themselves. Basically, the fact that you have upper and lower bound depend on the sign of the product of the two functions. So this is pointwise for each z. How can we use this? We can use this, rewriting a little bit equation 9, we can use to estimate the local covariance using the information about using basically the variance of the costationary solution, okay, and the local variances of the actual time series. And this is an alternative way with respect to the classic way, I would say, which is basically given in equation 11, where basically the local covariance is just a sum of cross spectra over scales, and can be estimated by plugging in an estimator for the cross spectra. We have an illustration for our stock data. So dotted lines are estimate obtained by using the costationary method for the two solution sets. So they look very similar, just shifted a little bit. And the solid line is basically the direct estimate. So in principle, knowing that there exists a costationary solution will let us use a piece of information which is not used by using the classic method given in equation 11. Basically, we are pleased to see that since the alpha times beta t is always negative for these actual is always negative for this example. If you look at these two, the top row of the two pictures, and you basically do the product for each time point, you see that it's always negative. So basically, this implies a uniform negative bound, a lower bound for the local covariance function. And this is, in fact, even if this is just estimate, it's basically holds for our example anyway. We can conclude basically that we have defined a new criterion to assess the relation between locally stationary processes. And we also derive some bounds for the local covariance function, and we show that existence of costationarity implies existence of these bounds. We can use these bounds to, well, actually, we can use the costationary solution to estimate the local covariance function using improved information with respect to the classic method. In some sense, a kind of conditional approach to estimation. We also derive a stationarity test, which has very good finite sample properties. I didn't show here, but it's very good for a time series in time series context. And also, I didn't discuss more applications because there is some ongoing work about it, but we are investigating now applications in economics and meteorology. But for instance, we can use also costationarity to forecast one-time series, which is perhaps difficult to forecast for some reason, even for data availability, knowing the other one and knowing that there exists a costationary relation between them. So forecasting is another possible application, and also we have some application in finance. I think we can show that using costationarity can lead to improve risk management techniques. I think I finished. Thank you.
I'm going to present the work Seasonal Dynamic Factor Analysis and Bootstrap Inference Application to Electricity Market Forecasting. This is a joint work with Professor Andrés Alonso, who is with Universidad Carlos III de Madrid, Professor Julio Rodríguez, who is with Universidad Autónoma de Madrid, and also with María Jesús Sánchez, who is also here, who is with Universidad Politécnica de Madrid. The points I will go on during my presentation will be the following. First of all, I will present some objectives and the motivation of this paper. Then I will go through some previous results concerning the methodology we are developing here. Then I will introduce the model that we are presenting, the seasonal dynamic factor model, and a bootstrap procedure developed to be able to make inference on this model. And then we will present a challenging application, which is forecasting electricity prices in the Spanish market. Finally, I will provide some conclusions. Concerning the methodology, the idea of this paper, the main idea of this paper is to extend the non-stationary dynamic factor analysis to be able to reduce dimensionality in vectors of time series which present seasonality. The papers that had been presented before this one, what they did is to deseasonalize the vector of time series that presented seasonality, and then apply some of the available techniques to reduce dimensionality in vector of time series that does not present seasonality. What we are going to do is to allow the common factors extracted for this high dimensional vector of time series to present multiplicative vector ARIMA model. And then we are going to introduce a bootstrap procedure to be able to make inference on the parameters involved in the model, and we are going to apply it to forecasting electricity prices in the Spanish market. For those of you that don't know how electricity prices are working nowadays, I have to tell you that in most of developed countries, the electricity markets are deregulated. This means that for each hour of the day, both the consumers and the producers submit their bids to the market, and then we define the marginal price as the price offered by the last unit that needs to be producing for the whole demand being satisfied. So this marginal price is that the one that we are interested on, and this is the price that we would like to forecast. Some previous models we have used to do this because this is a line of research that we have been developing through the last few years. What we focus at the beginning of our research is to focus on 1 day ahead forecasting of electricity prices, and we develop a very easy model, but a very accurate model to produce forecasts for the next day. So what we did is to make many different univariate models for the 24-hourly time series, and we combined all of them, and by means of a design of experiments we obtained the best one, a mixed model that was a combination of several models. But doing this, we were missing the relationships between consecutive hours, so the next alternative will be to build a vector ARMA model for this 24-hourly time series, but the dimension of this vector is very high. So the next step to not missing this relationship is to extract common factors. But in this vector of time series we have seasonality, so we had to develop a methodology that is able to extract common factors that present seasonality. So some previous results concerning dimensionality reduction in time series is this one. Peña box model in 1987. They presented a dimensionality reduction technique which is only valid for the stationary case, which is not our case. Then Lee Carter in 1992, they presented demographic application of some kind of dynamic principal components to forecast fertility and mortality rates. More recently, in 2004 and 2006, Peña and Poncello presented the non-stationary dynamic factor analysis, but it's able to deal with non-stationary vectors of time series, but not seasonal ones. That is the thing that we are introducing here. And finally, our application here is to extend this non-stationary dynamic factor analysis to the case in which seasonality is present in the vector of time series. We have also introduced a procedure, a bootstrap procedure, to make inference on all the parameters of the model. This is the vector of 24-hourly time series in the Spanish market from the beginning of 1998 till the end of 2008. And we are going to estimate the model for the first 10 years, and then we are going to do year-ahead forecast for the last one. Well, we are also going to give some results for the year 2004, because we have been working on this for several years, and recently we have updated the data. This is the model we are introducing here. The YT is the vector of M time series generated by a set of R unobserved common factors. R is much smaller than M, and FT is the unobserved common factors, and they can follow a multiplicative seasonal Barima model. A multiplicative seasonal Barima model. Then what we are doing is to decompose the original vector of time series into two parts, two orthogonal parts, the common part and the specific part. In the specific part we have a vector of specific components, which is m-dimensional, and its variance-covariance matrix, S, is a diagonal one. So what we are going to do to estimate the model is to express everything under the state space formulation. In the state space formulation, we have a first equation, the observation equation, in which we relate a vector of observed series to an unobserved component state vector. And in the second equation, what we are describing is the dynamic evolution of the transition of the unobserved state vector. So the natural way of expressing our dynamic factor model is the state space formulation. And what we are going to do is to estimate it by maximum likelihood using the EM algorithm. So we run the Kalman filter and smoother to calculate the log likelihood. Then we perform the E step, because we have to condition on the common factors. because we have also to estimate them because they are unknown. Then in the M step, we obtain the variance covariance. Q is the variance covariance matrix of the noise of the common factors, which is fixed to be the identity matrix, because if we don't do that, the model is not identified under rotations. Then S is the variance covariance matrix of the specific factors, which is a diagonal matrix. And then omega is the loading matrix relating the observed and unobserved common factors. And phi is the transition matrix. We repeat this loop till convergence is reached. And when convergence is reached, we have the estimates for the parameters of the model. I have to highlight here that due to the seasonality in the vector ARIMA model, we had to modify the maximization step because some nonlinear restrictions appear between the coefficients in the model. So we have to modify the M step to perform the estimation. So once the model has been estimated, what we would like to do is to make inference on all the parameters involved in model, and we have developed a bootstrap procedure for this purpose. So the first step is to estimate all the parameters involved in the model, the constant for the common factors, the transition matrix, the loading matrix, the variance covariance matrix of the specific factors, and also the initial conditions for the common factors. And then with this, we obtain the estimated specific common factors using the original time series and the estimated common part. Here it's important to say that we need a correction term that relates the variance covariance matrix of the specific factors to the variance covariance matrix of the estimated specific factors. All the derivations for this term are in the extended version of our paper, which is available in our website. And this term is important to say that can be expressed in terms of the estimated loads and the variance of the state variables. So we can estimate this correction term. It's important, this correction term, to be able to draw some resamples from the specific factors. And we use a similar correction term to obtain resamples from the residual of the common factors. And we use the resamples of the residuals of the common factors to obtain resamples of the common factors, bootstrap resamples of the common factors. And then, using the bootstrap resamples of the common factors and the bootstrap resamples of the specific factors, we are able to obtain resamples of the bootstrap resamples of our model. So we can generate B bootstrap replicates of our model using the bootstrap replicates of the common factors and the bootstrap replicates of the specific factors, in which is important, as I have said, to take into account this correction term. Once we have obtained the bootstrap replicates, what we are going to do is to estimate the seasonal dynamic factor model for each replicate. So we are able to make inference based on the percentiles obtained from the bootstrap distribution function of all the parameters involved. So apart from this, we are interested on calculating bootstrap forecasting intervals, and we have to slightly modify the procedure before described because we have to build some replicates, but taking into account the conditional distribution of future observation given the observed vector of time series. So what we are going to do is for specific factors and for the common factors, we have to fix the last observation, in each case the corresponding ones, and we are able to obtain future bootstrap resamples of the common factors and future bootstrap replicates also of the specific factors, and then using the observation equation, we are able to generate bootstrap replicates of the future observation, conditioning on the vector, the given vector of observed time series. So now that we have explained the model and the bootstrap procedure, we are going to estimate the model for the period between the beginning of 1998 and the end of 2007, and we are going to produce forecast for the whole year 2008. We are also going to show some results using the data till the end of 2003 to forecast the whole year 2004. So we are going to see that for different periods in the series, the forecasts produced are accurate. So what we are going to do is to extract two common factors. We have used the test proposed by Peña and Poncela in 2006. We have detected that we have two unobserved common factors, and the model we have fitted for these common factors is a seasonal Varima model with weekly seasonality, with the order in the regular part is one in the and also one in the seasonal part, and we have a seasonal unit root. So this is the model for the two common factors. We have to express this, the last equation I have shown, in the correct formulation under the state space notation. And once we have obtained some bootstrap replicates, we can see if all the parameters involved are significant or not. Here I am showing the constant of the model for the common factors, and as the 0 is included in the 95% percentile base interval, we can say that it's not significant, not the constant of the common factor, neither the constant of the second one. And we can re-estimate the model imposing this constraint, so we have less parameters. And we have also detected that the coefficient relating the second common factor to the first lag of the first common factor is also non-significant, as also the 0 is included in the 95% intervals. So we re-estimate the model imposing also that constraint. Once we have done this, what we obtain for the loading matrix, remember that the loading matrix is relating the vector of observed time series to the unobserved common factor. For the first factor, we have that all the loads are positive, but we obtain smaller ones for those hours in the night in which also the level and the variability of the prices is smaller, and higher loads for those hours in which both the level and the variance of the price is higher. And then the second factor separates between those hours in the night and those hours in the day in which the variability and the level is high. Here I show the two common factors obtained. If you remember the graphic of the 24-hourly time series, this is the common pattern they follow. And here for some significant hours, we show the electricity prices in the continuous line, and in the dotted line is the part explained by the common factors. Then, once the model has been estimated, what we are going to do is to obtain forecast for the whole year 2004, using the data only till the end of 2003, and also for another period, we are going to calculate forecast for the whole year 2008, using the data till the end of 2007. For the whole year 2004, we obtain a mean average percentage error slightly above 20%, and for the whole year 2008, we obtain a mean average percentage error around 17%. But we have to relate this to the 1 day ahead forecasting errors that are usually obtained by other authors, which are around 13–15%. So we have slightly above 20 and around 17 for year ahead forecasts. So very accurate results. And well, what I'm quoting here is the error we obtain with our mixed model in the Spanish market, in which we obtain forecasting error around 12%, but this is for 1 day ahead forecast. So for year ahead forecast, we have for these periods 21% and 17%. Here what I saw is that with using the mixed model in the long-term forecasting, the results we obtain are very bad, very poor results. Mean average percentage error above 45%. Using dynamic factor analysis without seasonality, 28%, and improvement we got when we include common factors that are allowed to follow multiplicative seasonal ARIMA model is we get a nice improvement. And here we saw the same results for the year 2008, in which mean average percentage error is around 17%. For some particular weeks, it's usually in electricity markets to provide some particular results concerning the third weeks in each month. And this is the third week in February 2004. So forecasting error is around 2 months, 16%. Here for the third week in May 2008. So forecasting error is around 5 months. And the mean average percentage error is around 11%. And here for the third week in November 2008, so forecasting horizon is around 11 months. The mean average percentage error is around 14%. And here what I'm showing is the forecasting intervals we obtain applying our bootstrap procedure. So we include also the uncertainty due to parameter estimation. And for the last week in May 2004, these are in green the real prices, and we have also the 95%, 80%, 70%, and 50% intervals. Finally, to conclude, we have extended the non-stationary dynamic factor model to the case in which the common factors follow a multiplicative seasonal ARIMA model with a constant. The constant has been included by means of an exogenous variable, so the extension to the case in which we have other exogenous variables like load or wind power generation or something like that is almost straightforward. We have also developed a bootstrap procedure to make inference on all the parameters involved in the model, and we also can compute not only point forecast but bootstrap forecasting intervals for the prices. And we have to highlight that this bootstrap procedure is valid for all the models that can be expressed using state space formulation. Finally, the results that we get for the Spanish electricity market are really accurate because we have year ahead forecasting errors around 20% or 17% depending on the year for long run forecasts, always bearing in mind that the errors for 1 day ahead are around 13%. And now our research is dealing with conditionally heteroscedastic seasonal dynamic factor model to allow common factors to follow also a gauge model in the noises. And we are also focusing now on dealing with the joint estimation of the model in the specific factors as well as common factors. And that's it.